Hello everyone, welcome to Tactica Imperialis and to the solutions video to the Newton's Laws Tactica Tutorialis question sheet. So this is for only those who had a go at the questions or who just want to see the full working of how they were done. I know we did a worked example in the main video, but it never hurts to see some more. So hopefully you've had a go and you can mark your answers. Let's go through them, shall we? So, a few things to clarify right away before we get started, because I asked you to calculate a few things. So I asked you to work out the resultant force and the acceleration for each of the three systems that you have, where the acceleration is of course applicable, as well as which of Newton's laws was in play, and I told you to use the gravitational field strength of G equals 10 rather than 9.8. Now I think you don't have to do any calculations with that. Now, those of you who are GCSE students, this is not normal. This is what you'll do in Key Stage 3 quite often, but at Key Stage 4, we generally will use 9.8, and at A-level you'll get to 9.81. We get more and more accurate as we go. Just a caveat there. So, first question, we have a mass of 10 kilograms, which gives us a weight of 100 newtons downwards, because weight as a force always acts down toward the center of the earth. We are then told that there is an air resistance or drag of 20 newtons upwards. So I'm not going to get this perfectly to scale, but you should have, if you had a ruler, where I have a smaller arrow going upwards labeled as 20 newtons. Now that's not 5 times that, but it should be if you've drawn it accurately into scale. So what we have to work out now is the resultant force. So resultant force equals, so we have 100 down and 20 up. So we subtract 20 from 100. Now reminder, if I had 20 down and 100 down, I would have 100 plus 20. The subtraction is because they're in opposite directions. They're opposite pairs to each other, so I take them away from each other. Which means that my resultant force is going to be 80 newtons. 100 take away 20 downwards. Because force, especially at GCSE, is what we know as a vector. So we have to give the direction of that force as well as its size or its magnitude. Now the second part I asked you to work out, if applicable, was the acceleration. And this is from Newton's second law. And that, if you remember, was F over m. Now F is this, because remember, the only force that is causing the object to move is the resultant force. Everything else has been cancelled out. What's left is the resultant force to move the object. So my acceleration is equal to 80 divided by the mass of the object, which, as we said, was 10 kilograms, and that gives us a value of 8 meters per second squared. That's written in power notation. If you wrote it as meters per second squared, that is equally applicable. So 80 newtons, 8 meters per second squared. Again, acceleration is a vector, so I'm going to give its direction downwards, and that is a full, complete answer. So that's question 1. Now I'm going to clear the board and we're going to have a look at question 2. Okay, question 2 is a little bit more complicated in many ways, because now we've got 4 forces in play. So, first one, we have the object's mass, which we are given as 25 kilograms, which, because we're using G equals 10 and weight is mass times gravitational field strength, we have a force of 250 newtons down, and that is the weight of the object. Now, by Newton's third law, we are told that there is a reaction force of 250 newtons upwards. Now, you can draw this here, or you can draw this here. I'm going to draw it here. And I've tried to make it the same size on both sides, because remember, by Newton's third law, we have an equal and opposite reaction. So they're equal and opposite to each other. Same size, the arrow should be the same length. We're then told we have a push force of 300 newtons to the right. And this arrow should be slightly longer than these two arrows because 300 is bigger than 250. And finally, we're told we have a frictional force of 300 newtons to the left. So again, roughly. Now you might have wanted to draw your friction like here-ish, here's fine. So 300 newtons to the left. Now, let's calculate our resultant force. So our resultant force has got to be worked out in two separate bits. We've got the up and down and the left and right. We're going to resolve this as two separate calculations. So, resultant force. Left and right, we have 300 right and 300 left. Minus 300 to the left because they're in opposite directions equals 0. What about up and down? Well, we have 250 up and we have 250 down. So opposite direction, so do a subtraction. 250 take away 250 equals 0 newtons. Therefore, resultant force equals 0 newtons. Don't need to give a direction because there is no direction. And then that means our acceleration is 0 meters per second squared. The object is not accelerating. Now this could mean one of two things that I think I've talked about in the main video. So this could mean that our block is not moving because it is stuck in place and we're trying to push it and the friction is too much and it won't go. Or it could mean that our object is moving at a constant velocity because if the forces are balanced, the state of motion cannot change. That is Newton's first law. So if the object is already moving, so it's just moving along like this at a constant speed, the forces on it are balanced because it is not accelerating. It is not changing its state of motion. So it carries on at a constant speed. And that is also a valid situation. And something that's very often missed is that people think no resultant force, no acceleration, okay, it's not moving. Probably, but not necessarily. Just want to make sure to stress that one more time in this solutions video for you dedicated people who came here. So, that's that one. Now we're going to have a bit of a harder one, and we're going to take a look at question 3. Okay, question 3. Please ignore my absolutely fabulous drawings, as I'm sure you did in the main diagram as well. Yes, it's physics. We don't need to draw super accurately. This is more than enough. So, first off, we're told we have a mass of 500 kilograms, which means we're going to have a downward force, a weight, of 5,000 newtons, because again, we're going to use G equals 10 to simplify our arithmetic. We're then told that there is an upthrust force, so from pretty much the air underneath the plane pushing it up, of 6,000 newtons. So I need to make this a little bit longer. And that is 6,000 newtons. We're then told that there is an engine thrust force of 10,000 newtons to the right. Now, I can't fit two of this in, but I'm going to make it huge. 10,000 newtons to the right. And an air resistance of 4,000 newtons to the left. That is what we are told by the question. Now, this one, you have to resolve it vertically and horizontally separately, as we did in the previous question. Now, for the final answer, there are two ways that you can write the answer, and I gave a hint in there about the Pythagoras theorem. So if you're particularly up in GCSE, you might have met the Pythagoras theorem by now, and so you might have been able to do a bit more than people who are perhaps in Key Stage 3 and haven't met it yet. So, let's do the resultant forces, shall we? So, first off, resultant force for left-right for the horizontal is 10,000, take away 4,000, equals 6,000 newtons to the right. So, we have a resultant force there. Our resultant force For the vertical, the up down equals 6,000 up minus 5,000 down equals 1,000 newtons upwards. So those are our two resultant forces. I'm going to draw that down here. Our resultant force overall is 6,000 to the right and 1,000 newtons, that's 1,000 newtons up. So our overall resultant force looks a little something like not that, because that's curvy as flip. You will draw this with a ruler if you are copying out my solutions. I physically cannot draw a straight line on this board because this board is curvy. Is actually starting to curve under the amount of times I've written on it. Right, let's try this one more time. Bang. There we go. There's our resultant force. Had to cheat a little bit there, but that'll do. 6,000, 1,000. There's our overall resultant force. I'll come back to that in a moment. So that means our acceleration in the horizontal equals 6,000 divided by 500, because for Newton's second law, it's F divided by M, remember, for Newton's second law. And that is equal to, I can do this in my head, cancel that, cancel that, cancel that, cancel that. 60 divided by 5 is 12 meters per second squared to the right. And the acceleration in the vertical is equal to 1,000 divided by 500 equals 2 meters per second squared upwards. So same idea, but that would say 12 and that would say 2. Now, that for key stage 3 is probably as complicated as it's ever going to get. There's some huge numbers. I deliberately made them huge to make them a bit more realistic. They're still not realistic. But breaking it down, doing the horizontals and doing the verticals, and then calculating the accelerations using Newton's second law, that's probably as complicated as it will ever get if you're at key stage 3, unless your key stage 3 teaches you the Pythagorean theorem, in which case, fair play to your key stage 3, that's ridiculously difficult, but good luck to you. Now, let's resolve the Pythagoras problem for particularly our GCSE and A-level friends. So, let's do that. So I've left that solution up there. If you want to go back and copy it down a bit more, you can do that. I just want to make a little bit of space by rubbing off all the blue bits. That'll do. So, we know, I'll do this in red now, sort of the doom colour, that our resultant force is 6,000 to the right and 1,000 up. And we've drawn that as our triangle down here, which I'm hopefully going to draw a bit more neatly here. So, boom, boom, 1,000, 6,000, much better. Resultant force, and there's going to be angle here, which I'm going to call theta. So, what is the magnitude and direction of the resultant force? Not the components, the actual resultant force. Well, to work that out, you need the Pythagorean theorem and trigonometry. So, Pythagoras states that for a right-angled triangle, a squared plus b squared equals c squared, where you have c, a, and b. So the squares of the two short sides add up to be the square of the long side. Or if you like, the square of the opposite and the adjacent add up to be the square of the hypotenuse if we're talking in trigonometric language. So, RF squared is equal to 6,000 all squared plus 1,000 all squared. Now, I could do that in my head, but we're not going to. 6,000 squared plus 1,000 squared is 37 million. 37 times 10 to the 6. But that is the square of the resultant force, so we need to square root it. For RF equals the square root of 37 times 10 to the 6 equals, as you can see there, 6,083 newtons if we round it off. That is the magnitude of the resultant force. What about the direction? Well, for that, we're going to have to rely on trigonometry. So, trigonometry, I'm going to clear the little blue triangle in the corner because I've got a better one now. Trigonometry, I know I'm using a lot of maths today, has the old SOHCAHTOA trick. Hopefully, if you've seen any trigonometry at all, you've met SOHCAHTOA by now. Now, with the angles, what we've worked out, we could theoretically use any of these three to work out the angle. But this one, we've calculated ourselves, so let's not trust it as much as we trust the other two. So we're going to use the one that doesn't use the resultant force, which is the hypotenuse, which means we want this one right here. So that would tell us that tan theta equals the opposite angle to it is 1,000. And the adjacent angle, or the adjacent force, is 6,000, which means that theta is tan to the -1 of 1 over 6. Now make sure that your calculator is in degrees mode if you've got a calculator like mine. Tan to the -1, fraction, 1 over 6 says 9.5 degrees. Ish. So, what that tells us then is that our resultant force on the plane has a magnitude of 6,083 newtons at an angle of 9.5 degrees to the horizontal. Or you could equally say, and do your triangle slightly differently, to be 1,000 and... could you do it? No, you probably wouldn't for this one, but you could rearrange it a bit so that your angle is measured from the vertical, call it phi, where phi is 90 minus that, and you work it out that way instead. So you work out basically this angle, which would also be phi. So you work out that angle instead of that angle. Go with what the question says. Usually it works to the vertical, but I've done it to the horizontal here because it's a neater triangle for you to understand what I'm doing. So the acceleration, therefore, so A is equal to 6,083 divided by 500. I'll just put that back in. And now divide that by 500. So the acceleration is 12.2. Now I've sort of rounded a bit arbitrarily there, but we'll say that I've gone with that. 12.2 meters per second squared at an angle of 9.5 degrees to the horizontal. Again, this is about as complex as a forces question I think can really get. I don't know. There's probably something messier that you've seen before in a GCSE past paper, but roughly speaking, resolving forces, doing the Pythagorean theorem and trigonometry on it is as hard as a resultant forces acceleration Newton's laws question is probably going to get. And this stuff, of this idea of using trigonometry and using Pythagoras, is very common at A-level physics. In fact, I've been preparing a lesson very recently all about resolving vectors, which forces are, into their components to calculate their size. I'm basically doing this, but backwards. It's really quite clever, and you'll meet it a lot at A-level. So, something to take a lot of notes on if you're A-level minded in particular, or you're in triple science. And even if you're not, if this at all made any sense, or you can put together a solution for this, you've pretty much cracked it in terms of calculations involving Newton's laws. So, that is all for today. Thank you very much for watching. I do hope you've enjoyed this little solutions video, and the fact that I've pulled it out of the main video to save time, because this has gone on for like 20 plus minutes, which is nuts, just solving some questions. But that's the detail that we needed, and I'm going to continue this trend going forward of pulling solutions out of videos to let the main video lesson just flow. But if you are stuck with any of what I've just done, do let me know via the comments on this video. They are, of course, open as always. And thank you very much for your time. Thank you very much for your hard work in getting to this stuff. I really do appreciate it. And hopefully, I'll see you in the next lesson. This has been Tactica Imperialis. This has been Tactica Tutorialis, Newton's Laws, the solutions. And I'll see you all again. Bye for now.